Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW Gulf. Students, I welcome you all to your Triumph Ultimate Recap. And today, students, we are going to start with our new chapter that is going to be D and F block elements. Now, you very well know, students, that we are basically doing the revision part, that means the recap part. In this, we are going to cover the D and F block elements in the complete one short session, right? So what you have to do is you have to take out your NCERT, because see, when I'm talking about inorganic chemistry, okay, either it is of 11th or of 12th, NCERT plays a very, very important role. So what you can do is you can open up your NCERT, listen to each and every concept, and if you feel like, there are some points to underline, there are some points to highlight, do that in NCERT. Moreover, keep some, empty pages with you, so that if you have any new point to add in NCERT, you can write it over there and then staple it out, right? So this is the way you can do your inorganic chemistry with very ease, right? Now, ma'am, how are we going to proceed? What are we going to do in this complete session? So in this Triumph Ultimate Recap, we are going to finish our DNF block elements, students, and I'm going to tell you what is the sequence in order to complete the chapter, because this is a huge chapter though, and we have to complete this in one shot. So yes, I have brought some of the major key points over here that you can write down, you can create your short notes that can help you in your examination also. So basically, I would say this is a revision session, but also I would say it is a session that will help you in order to make your short notes for your exams, right? Okay, so let's proceed with DNF block elements in our Triumph Ultimate Recap session. So this is the sequence through which how we are going to proceed with today's class. The very first is we are going to do the general introduction part about the D block and the F block elements. Moreover, we'll be understanding in the general introduction about the transition elements, right? Other than this, students, we'll be moving on to the electronic configuration of D block elements. First, we will be completing the D block and then the F block ones. So, electronic configuration of the D block elements, then comes the general properties of the transition elements. So, I will be letting you know what is transition elements in the introductory part only. And then we'll be moving further with the properties section, right? Then comes out to be some important D block metal compounds that we have to study, such as, potassium permanganate, K2Cr2O7. So, we are going to do that as well. Next, students, comes out to be your F block elements, also referred to as the inner transition elements. In that, again, in the same way, just as we did for the D block ones, we are going to do in the same way for the F block ones. We'll be doing the physical properties. Then comes the electropositive character, ionization energy, magnetic behavior, right? Radioactivity, oxidation state, their uses, and then the actinoids one. So lanthanoids and the actinoids, all of these categories will be covered in this one-shot session today, right? Okay, so let's start with the very first topic of ours in our today's session. What is the general introduction with regard to D and F block elements? Now see, students, you should always know that whensoever we have a partially filled electronic configuration in their combined state or in their common oxidation state, partially filled configuration, they will be referred to as the transition elements. I am talking about partially filled d orbitals, okay? So they will be referred to as the transition elements. And whensoever we have a complete configuration, completely filled orbitals, just as in the case of zinc, cadmium and mercury, they are not transition elements, but yes, they are also D block elements, because the last electron enters into the D subshell. So what is the transition elements, in which we can say that there is a partially filled D orbital configuration, right? So when it is so, in the combined or in their oxidation state, commonly oxidation state, that is your transition ones. But if I'll talk about, zinc, cadmium and mercury, they have completely filled electronic configurations and the last electron enters into the D subshell. So they are D block elements, but they are not the transition elements. Now let's read more about it. So in the modern periodic table, elements are classified on the basis of the electronic configurations into S block, P block, D block and F block. Yes, let me once show you the periodic table so that you can also get an idea about it. Yes, everyone? Okay. So this is basically your periodic table, students. Let me, yeah, okay. So I have just widened up. So see, students, over here, this is your S block elements. These two basically groups comes under the category of S block elements, group 1 and group 2. Then if I'll talk about these groups over here, group number 13, 14, 15, 16, 17 and 18. From 13 to 18 lies your p block elements, and if I'll talk about your group d block elements, group number 3rd to group number 12 comes under that category of d block elements. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, these are transition elements. But if I'll talk about zinc, cadmium, mercury over here, they are not transition elements, but they are d block elements, right? Let's talk about the f block elements over here only. So you can clearly observe in these series we have here 57th atomic element over here. 57th is lanthanum, and after lanthanum we have hafnium, which has an atomic number of 72. So after 57 then 72, where are the other elements that lie in between them? So they are basically placed below, which are referred to as the f block elements, and they are referred to as lanthanoid series. Why? Because before the start of the very first element cerium, there was lanthanum, so the series name is lanthanum series. Then if you'll see from 89 over here, a jump to 104th is given over here. That means here is actinium, and after that we have rutherfordium. So the in between elements are placed as actinoid series under the f block elements. Now let me tell you students, lanthanum and actinium basically they are d block elements, they are not f block elements. F block elements starts from 58 to 71, 90 to 103. Okay, so 57 and 89 will lie over here only. So this was about the periodic table. I guess everybody has this at home. Yes, okay. Now let's come back to our part. Now we very well know why the elements are classified as S block, P block, D block and F block, because the last electron enters into that particular subshell, right? Okay, so the elements whose differentiating electron basically enters an n-1 d subshell are referred to as your D block elements. Next part, the d block elements in which the atoms or stable ions have incomplete d orbitals are called transition elements. That means the partially filled ones, right? Next comes, that means that does not have the fully filled configuration. A typical transition element shall have an incompletely filled d subshell either in their elemental state or in their chemically significant oxidation state. So I told obviously this thing to you already, that either in their elemental state, their combined state, or in their commonly oxidized state. If you'll see, it's basically mentioned over here that if they have incomplete d configuration, that means partially filled, they are transition ones. All the d block elements are not transition elements, but yeah, transition elements are d block elements. So zinc, cadmium and mercury are not the transition elements. Let's move on to the next part. Now we have electronic configuration, students. Electronic configuration is very simple. That is basically ns1 to 2, n-1, d 1 to 10. Now that means you basically know that we have 5 d orbitals. So one orbital contains 2 electrons. That means total of 10 electrons can be filled in the d orbital, right? So this is what is written, the general electronic configuration they have given you over here, right? And yes, there are some exceptions, though we are going to start and we are going to say there are a lot of exceptions in which we shall be observing that there can be a case where ns1 to 2 is not observed. There can be a state of ns0. So why does that happen? In order to attain stability, you will come to that part, no need to worry. Okay. Let's move on to the next is general properties of the transition elements. So we'll be understanding about the transition elements properties. See, basically they have different properties than the other ones. Why? Because they have small atomic sizes, large nuclear charge. Now what is a nuclear charge? Charge exhibited by the nucleus on the outermost electron is nuclear charge, right? And the presence of unpaired d or electrons, they can show different properties. So the very first is variable oxidation state. They can exhibit different oxidation state. D block elements, students generally have +2 oxidation state, but yes, there is again an exception over there as well. You will be observing that scandium basically does not exhibit that. Moreover, the highest oxidation state is +8. That is exhibited. And yes, F block, for F block elements, the common oxidation state is +3. Then comes out to be next properties is magnetic properties. Other than this is formation of colored hydrated ions and salts, alloy formation ability, catalytic properties, complex forming ability. So these are some properties that the transition elements exhibit. So let's start with the very first property that comes out to be the melting point and the boiling point. Let me tell you. The very first thing, if I'll talk about the 3D series over here, students, you should know that melting point always depends upon number of unpaired electrons. Number of unpaired electrons. More the unpaired electrons, more will be the melting point, right? Also it depends upon the metallic bonding. So if I'll talk about over here, see, from if I'll talk about 3D series, from scandium to chromium, you will be observing that number of d electrons are being increasing, number of unpaired electrons are being increasing, so melting point will increase. But in the case of manganese, many people will say, ma'am, it has basically d5 configuration, no? So that means 1 electron in each subshell. So why does not it has highest one? Why it is being decreased in chromium and Fe? Though chromium also have basically it has 3d5 4s1 configuration, all unpaired electrons. But in Mn basically over here you will see that here it is 3d5 4s2 configuration. There is 4s1 3d5, there is 4s2 3d5. So over here you will be observing that though it has it is already stable. It is already stable, students. You should know that melting point is dependent upon metallic bonding, and if it is already stable, why it will let its electrons to go and participate in any kind of bonding stuff, right? So that's why it is going to have less value than chromium and Fe. And then, as you know, from iron to zinc, again the number of unpaired electrons will keep on decreasing because more and more electrons are going to add up. So unpaired electrons are going to decrease, not electrons. I'm saying number of unpaired electrons, right? So that's why melting point will decrease. Now see, the melting and the boiling point of the transition elements are generally very high. The melting point of the transition elements rise to a maximum and then fall as the atomic number increases. Okay, manganese and technetium have abnormally low melting point. Manganese I already told you, right? So this was about the melting point order from the 3D series, students. Clear, everyone? Everybody please take a minute, write this down so that I can move on to the next part now. Yes, everyone, please write this down so that I can move on to the next part. Okay, let's see the next part now. Now comes enthalpy of atomization. Now, what is enthalpy of atomization? Let's understand this. See, we very well know that all the elements, due to the presence of unpaired electrons, will participate in metallic bonding. Now, let us consider we have a structure which in which each and every molecule shows metallic bonding with each other. Each and every atoms are showing metallic bonding with each other. So amount of energy, amount of heat required in order to break that bond, in order to break the metallic bond between two atoms, that is what is enthalpy of atomization. Clear? So let's discuss about it. The metals of the second and the third series, that means let's talk about the 4D and the 5D series, have greater enthalpies of atomization than that of 3D series. Okay, this is important factor indicating for the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition elements. So yes, enthalpy of atomization is more of 4D and 5D series in comparison to the 3D series. Again repeating, enthalpy of atomization is that heat required in order to break the metallic bond between the two atoms. Yes, everyone? Okay. Now let's talk about the next one. We have atomic and the ionic sizes. It's very interesting and the very important part if you are doing. So basically this is the 3D series, students, right? From scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So if I'll talk about the atomic number, it is 21, 22, 23, 24, 25, 26, 27, 28, 29 and 30. So see, students, what happens generally when we are moving along a period node, generally what happens, this is the general order. Nuclear charge will increase. Now again repeating, what is nuclear charge? The charge exhibited by the nucleus on the outermost electron is the nuclear charge. When nuclear charge increases, size automatically decreases. Why does this happen? Because if nucleus is exhibiting some force on the outermost electrons, it is pulling the electron towards itself. So the distance from the center to the outermost shell will now decrease. Hence the size is going to decrease. This is the general order. General order, I am repeating. But it is not true. It is not true in this case. Why? What happens over here? From scandium till manganese, what are you going to see? The same step. Yes, ma'am, nuclear charge will increase. Nuclear charge will increase. Size will decrease. This is the correct way. It is the correct way. Size will decrease. But what happens after Mn? What happens after Mn? You will be observing that over here in iron, cobalt and nickel, they will have almost equal size. They will have almost equal size. Why does that happen? Why they have an equal size over here, students? Because over here, two factors are working. One is nuclear charge. One is nuclear charge. And another factor is electronic repulsion. Another factor is electronic repulsion. So let's talk over here. See, we very well know basically the configuration. It is 4s2 3d1, 3d2, 3d3. Again 4s2 is also written over here, right? It will be 4s1 3d5. It is 4s2 3d5. It is 4s2 3d6. It is 4s2 3d7. It is 4s2 3d8. It is 4s1 3d10. And it is 4s2 3d10, right? So now observe, students, what happens over here. See, as you'll see in iron, cobalt and nickel, it is 3d6 configuration. That means 1, 2, 3, 4, 5 and now 6. See, 6. That means electron repulsion is now going to increase because here repulsion will occur. So nuclear charge and electronic repulsion, both factors are going to take place, due to which they will have equal size. Now let's talk about the last part. Over here, it is now going to increase. What is going to happen? It is going to increase. Why? Because over here, electronic repulsion factor will dominate. Why? Because it has 3d10 configuration, 10 electrons in the d orbitals. So electron will repel each other. That means the outer electron that was coming inside, the inner electrons are going to push it further. So the distance is now going to increase. So the order is, first it will decrease, then it will be equal, then it will increase. This is about the atomic and the radii, ionic radii. So the atomic radii of the transition elements lie in between those of S block and the P block elements. The covalent radii of the element decreases from left to right across the row in the transition series until near the end, when the size increases slightly. Yes. Now let's talk about, that was about period. This is about rows. So this is basically the 3D series, the 4D series, the 5D series. See, what general should happen, that from top to bottom, if you are moving, number of shells should increase. If number of shells are increasing, basically size will increase. So this happens in this case, from scandium, yttrium to lanthanum, it happens. But as you know, after lanthanum, we have hafnium and other elements are lied under the F block elements. So what is going to happen? Though the size is going to increase, but the size of 4D and the 5D series comes out to be same for these now. For group 4, group 5 and so onwards. Why? 4D and 5D will have same size due to which contraction? Yes, everyone. Due to lanthanide contraction. Due to lanthanide contraction, what will happen? The inner electrons won't participate in bonding. Yes, and lanthanide contractions will take place and the size is going to be reduced. Their size will be almost reduced. They will become almost equal due to the lanthanide contraction. Right, everyone? That's why this was about period. This was about group. Everybody just write it down so that I can move on to the next property of yours. I guess, students, you all have written the atomic radii and the ionic radii part over here for the period as well as for the group. Now let's talk about ionization energies of the 3D series. See, we very well know along a period, if we'll talk about, if nuclear charge generally increases, size is decreasing. And if I'll talk about ionization energy, students, how are you relating ionization energy? Just see, it's a very, very easy part. You have to see that all of the concepts, if you are moving from top to bottom, size is going to increase, ionization energy will decrease. If size is increasing, ionization energy is decreasing. So this is the concept how we correlate, that they're inversely proportional to each other. Right? So their ionization energies values are higher than the S block elements but less than that of the P block elements. They are less electropositive than the S block elements but more electropositive than the P block ones, right? So let's move on to the next one. Now, if you don't know what is ionization enthalpy, also let me tell you, it is basically the amount of energy required in order to remove one electron from the outermost shell. Yes? Okay, ma'am. Let's see the next part. Now, oxidation state, I've already told you that +2 is the general oxidation state that is exhibited by the D and F block elements. D block elements, not F block. F block have general +3 as a common oxidation state. But maximum oxidation state, what a D block element can hold is +8, right? This is what is told now. The transition metals exhibit a large number of oxidation states. With an exception of the few elements, most of them show variable oxidation state of +2. Scandium won't show that. Okay. Now, the existence of the transition elements in different oxidation states means that their atoms can lose different number of electrons. Now, we very well know that they are either going to lose from the SNS or from N-1D. Very simple. Right? So now, students, comes our next part, that is electrode potential and the chemical reactivity. Now, see, this is basically correlated with our electrochemistry part also, though we have studied in that as well. But yes, we should know about this also. So if I'll talk about the values, this basically is going to increase from left to right because ionization enthalpy, ionization potential value increases, right? Except zinc. Now, Cu cannot displace H2 from acid because it has a higher, the reducing power potential that we talk about, okay? And they have given you a certain values, standard electrode reduction potential values, okay? And they've even told you that if I'll talk about manganese, nickel and zinc, they have more negative values, standard reduction potential values, right? Than the expected ones. Now students, let's talk about the magnetic properties. Now this is also again, you have to see the paramagnetic and the diamagnetic behavior, which only and only depends upon the number of unpaired electrons, right? So in the paramagnetic case, if we are talking about, we will be saying that these are those substances that are attracted into the magnetic field when they're kept in higher magnetic field 1, right? So basically, paramagnetic contain unpaired number of electrons, right? And there are few examples for them as well. Diamagnetic is when there is a pairing between the electron, there is no unpaired electrons, that is diamagnetic, which are weakly repelled by the magnetic field and they are kept in the higher magnetic field, so they are being repelled over that spot of time. So they are stronger to the weaker field and they contain the electron pairs. As I've already told you, there is no unpaired electrons. So in the case of paramagnetic, you can even calculate the magnetic moment by root of nu and then mu plus 2, okay? So this is the way to calculate the magnetic moment. It is calculated in Bohr magneton. Right, their examples they have given you over here. Now comes the colors of the transition atoms. Now colors, who will exhibit colors? From D1 to D9 configuration can exhibit because they can do the DD transition. If they are completely filled, they cannot do that, right? So zinc, cadmium, mercury, again, they cannot show the colored complexes. So most of the compounds of transition elements are colored and the compounds of S block and the P block are almost colorless. Okay. Next comes the formation of complexes. So you will be observing that they are responsible in order to form the complexes due to the certain reasons. So there is a greater tendency of the transition metal ions to form complexes. Now why is it? It is because of small size. Next, high nuclear charge. Again, nuclear charge is the charge exhibited by the nucleus on the outermost electron. And ability of the vacant d orbitals of the suitable energy to accept the lone pair of electrons that are donated by the ligands. So it can form coordination complexes also. Various examples are provided to you over here. Let's see the next part. They can show catalytic properties also. Transition metals and their compounds act as a good catalyst, students. Now catalyst basically increases the activity of a reaction. That means it can occur in a lesser time in comparison to the one. That means it fastens up the reaction, right? But yes, catalyst once used will come out same as it is. It won't get consumed during the reaction. It will just help the reactant so that they can be converted into product. They have given you an example over here also, that Ziegler-Natta catalyst. They have told you an example with regard to the D block elements. Next part, students, formation of interstitial compounds. Now interstitial compounds, they can also help in that formation. Basically they form them with hydrogen, boron, carbon and nitrogen, generally they which have a smaller size. Now what happens is these atoms just get fit at the interstitial positions of a certain metal, right? So basically they are generally the non-stoichiometric and neither typically ionic nor covalent, and the common example they have given you. Now these smaller hydrogen, boron, carbon, nitrogen just fit into the interstitial positions and thus creates the interstitial complexes. Clear? Let's talk about now, they have told you what are the chemical properties and the physical properties of them. So they have high melting point, okay, then higher than that of the pure metals. Then they retain metallic conductivity, they are very hard in nature and they are chemically inert. Clear everyone? It's not insert, it's inert. The next part, students, is alloy formation. They can also participate in the alloy formation, the D block elements. So they have a various characteristics, students. Now, alloys are generally prepared how? They have given you steps. You can clearly see they can be prepared by melting a mixture of the metal or the components taken in a proper proportion. Simultaneously, electrolytic deposition of metals under the suitable conditions. Amalgams are prepared by grinding the metal with mercury. So in metallurgy also you have heard about these terms very well. Right, and even there are certain quenching is done. Now what is quenching? Alloy is made by sudden immersing in oil or water. Now this is certainly asked in exams, right? The next part. Now we are going to start with the compounds related to the D block elements. We are going to cover the two majorly important compounds. One is going to be potassium dichromate, that is K2Cr2O7. So its preparation method is very easy, students. So see, what happened? Chromite ion, basically chromite ion is FeO.Cr2O3. Okay, it is roasted with sodium carbonate, that is Na2CO3. Okay, and when you are doing the roasting process, see, we do have two processes, calcination and the roasting one. We are doing roasting process over here. So in roasting process, what are you going to obtain? See, in calcination there was, you know, limited supply of air, but here it is a proper supply of air. So what do you obtain? You obtain Na2Cr O4. Right, now the roasted mass that we have extracted, we are going to react it with H2SO4 and you are going to get Na2Cr2O7. Now this Na2Cr2O7 will further react with KCl to form your compound over here. This is what we want to obtain. Clear? Potassium dichromate. So now students, what are the properties? It is orange red colored crystalline compound. Generally the color they can ask you, and there are some reactions in which the color changes from orange to green, so they can ask you such as well. Right, and they are freely soluble in hot water, moderately soluble in the cold one. So this is the structure for the dichromate ion, that is Cr2O7-2. Here you can clearly see that it is Cr2O7-2, so they have drawn it properly, the ion structure. Chromium atom is surrounded by 4 oxygen atoms tetrahedrali, and it exhibits a geometry of sp3 hybridization. It contains 2 types of CRO bonds. Okay, it contains 2 types of CRO bonds. Next is OCR bond length. They have given you, no need to learn them, but yes, you can read it for once, right? Now if I'll talk about the chemical properties, students, it basically on heating will dissociate into what? K2CrO4. Okay, from Cr2O7 negative, from dichromate it will dissociate into chromate ion, that is K2CrO4 plus Cr2O3, and 3O2 will be liberated out. Clear everyone? And its color will change from orange to yellow. Do remember this part. Next is, this is chromate ion, which I've already told you, right? It will change from dichromate to the chromate one. So this is again a reaction of K2Cr2O7. When it reacts with KOH, it will dissociate into K2CrO4, right? And you can see in this we have this ion, basically Cr2O7-2, and in this we have this ion, that is CrO4-2. So it is changing its color from orange to yellow when it is converting from dichromate to the chromate one. Now I guess this is now easily you know this reaction, and this is generally asked in the examination also. Now comes the next part. It acts as a powerful oxidizing agent. Very, very important. You can put a huge star over here. Generally, question is asked that in acidic medium, basically it acts as a powerful oxidizing agent, and they can ask you when the reaction as well, right? Because here the question arises from the oxidation state. That what is the change in oxidation state? So it changes from +6 to +3 basically. Clear? And even ferrous salts are oxidized to ferric salts. When you will react this with Fe+2, Fe+2 will change into Fe+3. Clear everyone? Now we have its uses. Uses are just for the knowledge sake. You can read it. 2 or 3 uses you can learn out, right? So it is used as a volumetric reagent in the estimation of reducing agents, and it is used for the preparation of several chromium compounds as a cleansing agent as well. Right, now comes the next compound, that is potassium permanganate, that is KMNO4. Now if I'm talking about the preparation method, it is again an important one. If you want to read it, you can read it, because we generally use this chemical a lot in the laboratories and we have heard about it, but we don't know the method of preparation. This is the most important and well-known salt of permanganate acid and is prepared from pyrolusite ore. Now this you have heard in the metallurgy part also. Okay, it is prepared by fusing pyrolusite ore either with KOH or with K2CO3 in the presence of atmospheric oxygen or oxidizing agents such as KNO3. Okay, so you can clearly see this reaction. Basically, MnO2 reacts with KOH, it will produce K2MnO4, right? And if you want to see this reaction in detail, so MnO4 negative reacts with H positive and will form MnO4 negative, liberating MnO2. This MnO2 will further react with K2CO3, will form K2MnO4. Clear? And they are saying that the fused mass is extracted with water and the solution is now treated with a current of chlorine which is passed over. Okay, and even with ozone that is done, or even with carbon dioxide this is done, right? To convert the magnetite into permagnetite, to convert it into KMNO4. To convert K2MNO4 into KMNO4, we can either react with Cl2, with ozone, or with carbon dioxide. Clear? And you will get your final product, that is KMNO4. Now what are the physical properties? It is purple colored crystalline substance. Everybody knows that, right? It again has a tetrahedral shape, right? And let's talk about in detail that the magnetite and the permanganate ions are tetrahedral. The green magnetite is paramagnetic with one unpaired electron, but the permanganate ion is diamagnetic. Clear? Diamagnetic having paired electrons, paramagnetic having unpaired electrons. Uses oxidizing agent. It is being used as an oxidizing agent used in the qualitative analysis, used in organic chemistry. Okay, and alkaline potassium permanganate is also known as Bayer's reagent. Clear, everyone? So these was about the compounds of the D block elements. Now we are going to start with the F block elements, and it is very easy. In F block elements, I have already shown you with the periodic table that we were doing over here. You can clearly observe these are your F block elements. From 58th element to 71 we have lanthanoid. From 90th to 103 we have actinoid series, right? And here the last electron enters into the F subshell. That's why they are the F block elements, and their atomic sizes are almost quite equal to each other. We'll talk about it in detail. See, the elements constituting the F block are those in which 4f and the 5f orbitals are progressively filled, right? That means the F orbital is being filled. These elements are the members of group number 3. Now this question is generally asked. Many students just get confused. If they'll ask you what is the group, they will answer that either 6 or 7. No, it is 6th period for lanthanoid, 7th for actinide, but the group of both of them is this one. Third group. Here. Third group. They are separated and written down, right? So the F block elements comprise of two series, lanthanoid series, the 14 elements which contains, and the actinoid series, right? So total elements they can ask you. Now here is the lanthanoid series, you can clearly see, and their electronic configurations are also mentioned over here. Last electron enters into F subshell. So from cerium it is going to start. This lanthanum basically is a D block element, after which it starts. It is 57, it is 58, right? So from 58 it starts, 57 is in D block. It is named after the name lanthanum, right? So these are the electronic configuration, you can practice it out. Now starting with the physical properties and the chemical ones. Density, they have a density ranging between this value. Density generally increases with increasing atomic number. Just remember this thing. No need to learn the value. If I'll talk about the melting point and the boiling point, they have a higher melting point, okay? And if I'll talk about cerium, basically it melts as a higher temperature, and cerium is a hard as steel. So this is some of the exceptions that I've written over here so that you can learn it out. Next part is, let's talk about ionization energy. So they have fairly low ionization energy value, students, in comparison to the alkaline earth metals. Their values are quite comparable, if you will talk particularly about calcium. Abnormally low values of the third ionization enthalpies in the case of lanthanum, gadolinium and lutetium. Now what is third ionization energy? First you will take one electron out from the outermost shell, you'll give energy, that is first ionization energy given, so that first electron can be liberated out. Then you will give second, then you will give third. That means the third electron that is being liberated out, that is third ionization energy, right? So now comes magnetic behavior. Again, the diamagnetic, the paramagnetic. Paramagnetic will be seen when there will be unpaired electrons. Diamagnetic will be seen when there is paired electrons, right? So lanthanide ions generally show paramagnetism due to unpaired electrons in the f orbital. They are generally showing which kind of behavior? Paramagnetism. They have given you certain example, but the ions of lanthanide, which are La plus 3, Ce plus 4, okay, Lu plus 3, they are diamagnetic in nature. That means they have completely filled and the paired electrons. Clear? Now students, radioactivity, all lanthanum except the promethium and samarium. Now this is important, this is asked again and again. These are non-radioactive in nature. Let's talk about oxidation states. In oxidation state, generally they will have +3 oxidation states, the F block elements, okay. So the common oxidation state already told you is +3. Lanthanide can also exhibit +2 and +4, okay, in solution or in their solid form. And this oxidation state values changes due to the unpaired electrons, right? Clear, everyone? Now let's talk about the uses. They form alloys easily with the iron. Mish metal is an alloy. Now this we have heard in the metallurgy chapter also. Similarly, they have given you the different alloys which is basically used as a devices. So you can learn any of the two uses. Let's start with the actinoids one. Actinoids one are present below the lanthanoids one in the 7th period in the group number 3rd. These elements in which last electrons enter into 5f orbitals. Okay, they are the radioactive elements, and earlier members have relatively long half-life. Now half-life we have understood in chemical kinetics and depth that the radioactive elements exhibit, and later ones have half-life value ranging from a day to 3 minutes for lawrencium. Clear? Now students, moving on to these are your lanthanoid series, which are starting from thorium, again from element 90. 89 is not included in this, 89 is included in the D block element. So this is the general electronic configuration which you can practice on your own. Now comes the uses of actinoid. Thorium is used in atomic reactors and in the treatment of cancer. It is used as a nuclear fuel, uranium basically. Okay, so these are certain uses for this as well. Now students, as I've already told you that D and F block elements basically chapter is a huge chapter. So what you can do is I've just taken over here the important key points that is required for your examination. But now your work is to open up your NCRT, take out your notes and take a quick review, because see what happened is I cannot cover in one short lecture in a short interval of time the complete chapter. But yes, I can tell you the important key points which I've already told you in this chapter. So you can revise the important key points and then you can solve questions based upon that. So when you will be doing the important key points and applying on the questions, you will get to know that how questions are generally asked in the examination, right? So now students, we shall be meeting in the next lecture. Then keep smiling, keep learning. Thank you so much and have a good day everyone.